Okay, hello guys. Today theme of our preferably last lecture is language of quantum.
Never say never.
Never say okay. Never say never. So, the first of all, in short, what is language and why the language that we have is the language that we have, right? So we have like different brains, right? And each brain of the person A or person B, they are formed in different life experience. Both. Each is unique. Each of us is unique. There are lots of differences, and what this uniqueness come from? From the actually like location, time, right? Circumstances, everything, all around. The whole history. The history of A and history of B are different. In the generally, these things that in the whole they call context, like the form of localization, total localization, all the context of your life, including history, all the things that everything like this. So, if you take A and B without context, and context may include also like genetics, so the formation of the brain, organization. If you take totally the same formations and everything, genetics and everything, and no context, right? So you will have A and B, A equals B in this case, right? So the context, actually, what I want to understand, that context forms what we know as localization. Context localize A. Context define A or B. The context of its own life of A or life of B. All these contexts includes history and everything. It forms actually localization of A and all localization of B. So they differs because of the context is different, including of course genetics and everything. That's understood? Its context is the same as if you think about like some mathematical so-called like field, right? Which is like some function which depends upon the x, y, z, whatever coordinates, right? Mm-hmm. So x, y, z and whatever, like t, whatever, many of them, right? Many dimensions, maybe infinite dimensions. They give this context in which we see this this value of f, value of function. This is the context, actually. So in our case, the case of language and communication between A and B, right? The context is this x, y, z, blah, 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 whatever. This is localization. This, you understand that. You should understand this thing. So when you try to communicate, you try to send some message, like A sending some message to B, and like we're saying, like sit on, or without articles, like sit on chair, right? Whatever sit means, whatever chair means, these things are dependent on context. Because sitting, maybe for A it means like crossing legs, for B means like legs like this or whatever. Like sitting may be very different in understanding of A and B, right? Maybe even opposite totally. Because A and B are formed in different contexts and different histories. The same thing for chair, like for this chair, maybe when he says sit on chair, he means something like what we usually have on the chair, like four legs, right? The back, chair, right? But this for B, he never saw this chair, but he sits on something. He regularly had experience of sitting. Maybe he has in his mind something like forest stump, you know, this wood stump. I'm correct, right? In the whatever stump. So he's sitting on the stump. The same thing for table. So everything is different, but for some reason, this word or sentence, like this word chair, right? It's somehow understood. So when A says sit on chair, B understood A. And actually he did something that resembles somehow sitting on somehow looks like chair, right? B may sit on the stump, right? But it's actually they're very different. This is maybe understandable in regular communication because we live in very similar similar circumstances, like we have similar chairs and everything. But if A and B are specialists, we call specialists, right? One specialist one and special two. This guy works, for example, like quantum field theory, and this is like biologist, or maybe how does it, kitchen guy, kitchen lady,
Chef.
or maybe chef, whatever, like maybe homemaker, like home taker. Oh, what's the term for this?
Homemaker is usually what they're
Homemaker, right? So, and they want to speak with each other. They don't have even similar terms, right? Because this will speak on a special language, mostly mathematical. This will talk on their pots and whatever, and, other like spoons, forks, whatever, right? And very different to understand. But it may happen that we agreed to use the same terms, like same words, like chair, right? But and maybe not only chair, like for example, like take.
What?
Take. Like we agreed that we use this word take.
Okay.
Okay. But what it means for take? Take here, it's like take a fork, or take something, right? Take here, it may be the meaning may be very different in the quantum fields theory, and may be very different. But this word is has very meanings. This word take, and many words actually. There are multiple meanings. So it may have a very different meanings from that. Like it may mean, for example, like take time. The simplest thing, take time. You cannot take time like you take a fork, right? But we understand somehow, even with the not quantum field spheres, what is take time, right? So we're not taking, like you cannot take time, but still you can understand what it means because we have similar experiences. But if we don't, still we can, interesting enough, that still we can have some communication. How? If we understand that the world, remember this world is very, not only unique, but it's very universal. There is the existence of universality in this world, right? So everything may may disappear, everything can move, and here means different, and move here, and lots of other words. There's the whole system of words, which are actually have different meanings, but they all represent some similar system of relations between the things. Things may be different, but the words would be the same. So you use system of words, and that kind of subsystem of the language can be used to communicate between very different specialists, specialist one and special two. And would this communication be meaningful or not? It would be, because remember what I'm talking about, that the things, they represent some abstract symbols, right? They can represent not only things, particular things, but also relations between things in a correct way. They're like a play in the theater, like the symbols are the actors that play in the theater that actually resembles the real situation in some very distant, maybe a position, space-time, or field of understanding. It's just an abstract coming to this. Now let's continue a little more. We have, remember, we talk about neural networks, right? And especially the particular neural network which is coming, which may be considered a future hardware for the neural networks. This is quantum computing. Actually, considered like a hardware, right? And you know what means to have a machine-oriented language. What is machine-oriented language? It's language, right? So the system of symbols and relations between them, which is very good in representing the relations in the real quantum system, like the quantum computer, for example, in our case, right? So we have certain qubits or quanta, right? And we have certain relations between them, and we talk about this a little before in the previous lecture. we can think about some machine-oriented language, which is very closely oriented exactly to the quantum computing. And what language can this be? Like, if we think about it, what kind of language can this be? What is machine-oriented to the quantum computing and neural networks, because this is hardware for neural networks actually. So it would be, if we create that kind of language for, like for example, neural networks, we can use the same language for the quantum computing because it is neural networks actually, just the hardware for the idea of the neural networking. So what kind of language would it be? Remember, I told you that dialectics as a philosophical system, it's very much close to these relations that we have in quantum and in quantum computing, therefore. So dialectics is a philosophical system which is a good player, a good actor, and it presents what is called mathematically isomorphism. So it's one-to-one relation between symbol and thing, and symbol and relations. So we have certain symbols for things, right? Like A1, A2. We have certain symbols for relations, B1, B2, right? And all these things are very close to the real relations, the real things which we have in reality, like for example, quantum computing. So dialectics is very, very close to that. It happens this way. It not happens this way, just dialectic is a way of thinking about nature, about how the things are going in our world, in our universe, right? So it's pretty understandable. Then the philosophers were thinking on this for thousands of years, and they come to a certain system which is resembling in very good way the real situation in our universe. So we have dialectic as a system of which is using actually words, some terms, using normal words and everything. But the question is, can we create a real language that it would be dialectical? So it would be the system of this language. So you can say that grammar of this language will be, the rules of grammar will be the rules of dialectics. And at the same time, it will be like very close to this dialectical philosophy and represent in a very good way this machine-oriented language for the quantum computing. And it happened, actually, and Alicia should know that for different reasons, not that different, but still, that language was created, that kind of language was created. And because it is dialectical in its nature, and it is fractal in nature, so it is fractal, we can show like this. I already did that, right? It's recursive, like doubling over positions, right? So one root, so it's root, then it doubles to one and another, one in a position, then each thing doubles again, and like this. This is abstract tree. It can be not doubling, can be more, but the easiest way is double, and it can be emulated by doubling. Anything can be emulated by this. So this is the simplest thing of fractal as it is, and dialectics is the dialectics tree is like this too. So when how this thing works? First of all, you can see that it's very symmetrical. That is called self resemblance, remember, of fractal thing. Each thing here is very similar. You see three links, right, from each node, 3 links to the other node, right? Here again, 3 links. Each has 3 links, right? Can we think something under the root? Yes, we can. It can be doubled too, and we have totally symmetrical situation in all directions. In our usual case of the tree, this is the ground, right? So we have root system, and we have upper system of leaves and branches, right? So it's the same. Tree is actually growing up and down. The same thing is for the brains, for everything, except that the number of links may be more than 3, right? But again, this system is can represent anything, because you can look not on this simple node like this, but in more complex node like this, right? And it has much more connections already. So just a little increasing the size of the node, right? You see, you'll have the same symmetrical system of such nodes, big nodes, but they are connected with much more links than just 3. So in this case, the system can represent in multidimensional, even infinite dimensional system, the same way how it represent everything. And that was what actually dialectics do. So now it's just general way, right? So how this language was formed, the grammar, the rules, and of course the rules of grammar will be the rules on how these symbols play, how they act to represent certain things in our world, right? How they act, really. So, and the thing goes like this, like the usually goes in threes. It in Hegel's system of dialectics, they call triads or triads. I don't know what's the right pronunciation.
English triad.
Just trinity, three things. Triad, yeah. So triads.
It could also be triumvirate.
Yeah. Okay.
But a triad is a Chinese mobster.
Okay. Okay. Yes, right. They have because Chinese are smart guys. Their philosophy is dialectical too. They have yin and yang. You know these things, right? This is their like yin like this or this like this. I'm not sure, but they're dialectical oppositions, and they see from these positions they see the whole world the same way. How like European dialectics. Not actually, it's not even known what's the origins of dialectics. Is it probably origins are actually Oriental, not European. Europe is more young civilization actually, so most of these ideas of opposition and everything came probably from Orient, from Indian or more particular Aryan, the Aryan civilization, and or Chinese or today or together. Nobody knows for now. Exactly. So triads, yeah, maybe it's their name. Yeah, they use it rightfully, right? So what do we have in language? A language is like regular language, is formed of sounds. It's called phonemes, right? Phonemes, they are connected into syllables. Syllables, right?
Yeah, there's something.
Syllables, then words, then sentences, whatever. And each of this is a sound. Phoneme is a sound, syllable is a sound, word is a sound, right? So this is already universal. They're all sounds.
Mm-hmm.
Each sound has a beginning, the front, the becoming, and the end, like the sound ah, right?
Mm-hmm.
So you may say like not stressed ah, then stressed ah, big one. So like to pronounce simple. So this is phoneme, stressed phoneme, this is again phoneme, and this is a syllable already. Or you may say word, right? You can connect them to do whatever. You can do something else. You remember these all are universals: becoming, disappearing, right? Then transformation from becoming to disappearing. This is time, right? From disappearing to becoming. This is, what's the word? Возрождение, как там называется?
Rebirth.
Not rebirth, just
Reincarnation.
reincarnation, is something like this. Reincarnation or reservation, but reservation dynamical. It's not like static, right?
Yeah, resurrection.
Resurrection, yeah, resurrection. Yeah. Or resurrection, sort of that. And actually this thing, if it's this called time, this is actually space. If you look around, everything is actually saved in our space around, and space is all in past time. I think we will talk a little about this, right? And this goes very far. Not becoming and this one, but then there comes intonation. So this would be going up like ha, right? Or R goes down like and something in the middle, right? And also you can have like these things. So up, then sound, then down, and all kind of that combination. Then come this all are vowels, right?
Vowels.
Vowels. Then come consonants. And consonant actually different way of pauses between the sounds. So you can pause R, then pause, and then R, right? But also you can pause by putting something that interrupts the sound of R. Something that interrupts. And this interruption is actually consonant. Different types of interruptions are forming consonants. But anyway, and then you go syllables, words, and whatever. So this language is formed totally on oppositions and transformation of oppositions to each other, in total agreement with this system of dialectics. And what it gives you as a result. It gives you the language, which is by definition, by construction, it's very close to the quantum system, so the computer system, because it's based on laws of physics. The laws of physics are based on dialectics. And the base of everything, if you remember our previous lecture in physics, there is a loop. If you remember, there is time and space. This space is anti-time. That kind of loop. And this loop is called quantum. So this time and anti-time loop, this is what we know under the name of quantum, actually. And all the features of this quantum goes from this opposition, time-space. In a certain way, sometimes they say that this loop is actually what we call leap, right? Because with the time, we jump over this space. So the quantum is here, and then it jumped over space. And this is sort of a paradox. I think I mentioned it. There's Zeno paradox of arrow, right? Arrow should be in one place in one time, but actually somehow it goes to another place. And to understand this, you need to consider this paradox. So it's a leap, it's a jump from point A to point B. So this is based on this. So it is very close to what we call machine-oriented language. And machine-oriented language of quantum computing and neural networks. So it's very close to this system and to this system because they are very similar to each other. Interesting enough that this language that we're talking about, it was created not because of this. It was supposed to make people smarter. Smarter means much, much, much smarter. Actually, this language is supposed to make people real geniuses. And there are many, many features of this language that actually says that yes, it can do this, but you should learn it from the beginning, you know, from the childhood. So your mother should teach you, but in this way, mother should know this language. So it's sort of a wrong circle. So that's why this main problem is not overcome yet. So we have a language, people can learn it. Actually, the main things of this language can be learned like in 1 or 2 weeks, and people can talk with this language. And not only people, different specialists. Okay, I'll talk a little later. So what I mean under this, that this language was actually created for people. And now, if we think about people, remember that brains are neural network. So this machine, so-called machine-oriented language, actually it is human-oriented language. So the closest to the human, how humans think, this language is exactly that. So it may be used by neural networks and quantum computing, and it may be used for humans. And then the question is, who win, right? At the end. So it depends upon how humans are how humans can learn this language, how they can use it, and everything. So that's one of the questions. And now regarding these features, little features which that goes from this language, for example. So remember, we have two brains, like brain A and brain B. So, and for example, this brain is specialist 1, and this is specialist 2. And they, like for example, they don't have too much in common, except that they're human. They're both human, for example. They may be not even human, but for example, they are human. So this specialist is, for example, talking about, like, let it be quantum specialist, right? So he's specialist of quantum networks. So when he's talking about moving of quanta, he says that quantum goes from one position to another position, overcoming some space interval. So what happens in this language, what happens with the quantum, that quantum actually is transformed into space form, and quantum is considered as a time form. So this time part of the loop, then it goes to the space part of the loop. So you can look at this loop, remember this loop, from both sides. This is time and this is space. So you can look from here or from here. So here we see it like from time side, and here we see it from space side, and then it goes back to time. And this is quantum, in quantum theory it is called movement. So we have movement, physical movement. And we can talk about this. This is actually written in special operators. They're called supersymmetry operators. And this form time form of quantum is called Fermi quantum, and this is called Bose quantum. And this again Fermi. By the names of the guys who actually discovered these things and wrote equations and everything, right? Fermi, one of the physicists, Bose is another physicist. So, and this thing is called supersymmetry because the time when they discovered this, the physicists discovered this, it was very exciting for them, right? So something amazing because Fermi particles, Fermi quantum, are representing matter, what we call matter, like hard things. All around is made of matter. Electrons, protons, neutrons are all Fermi quantums. But space, it is something like field. It is everywhere. It is a field. It's not localized. Like electromagnetic field is a space spread in the space thing, right? Something very different from what we think about the particle. So in this supersymmetry, what happens actually? This localized particle, it is transforming into space, which is not localized at all. It's everywhere, and then back to the localized. So it looks like that particle actually dissolves into space and become a field, and then suddenly it gather again in the other point. This is point A, this is point B. And both particles are totally identical. This is another dogma, physical law, fundamental physical law, that like all fermions, like all electrons are identical, totally identical. But it appears to be in the other point of space and time, which is, if you remember, it is circumstances, it is the context. Socially, it's the same, so it's the same particle, identical, but it appears to be in different contexts, different situations, simply. And that's why we call these different coordinates in space and time. So this thing of the content is very, very important. You will see why. So this is for this specialist A. Now specialist B, right? for example, he can be an economist. An economist, they're talking about production, the trade, right? All these things, and the goods, right? So for economists, there is good one, good. Then it goes into money, and then it goes into good two, right? So you sell, get money, you buy another good. This is the circle. This is the circle of movement, right? T to T. This is the circle of goods or production. The same thing, if you product something, you go first from money, it's investment, right? Then you produce something, good, this is there's a labor included here, and then it goes to, again, you sold it and you get money again. Money to money or good to good. There are two circles, two sides of the circle. Exactly like this, from time via space to time, or you may go from space via time again to space. And remember, there's Fermi Bazet, right? Field and that. The same thing happens here. Believe it or not, there are lots of features that actually resembles this and this. So, but the main thing that is the same, if you try to use it mathematically, the same equations are working here and here as well. Same mathematics. This is one of the small pieces of this fractality of the whole world. You can apply the same picture to anything everywhere, and you will see the same thing. How it happens in language. And the language, by the way, of course, it is called dial from dialectics. First of all, it is your freedom of denotation, right? If I correct the term, using the term.
Denotation in the sense of you are free to assign whatever sound
Yeah.
you want to any
Yes.
meaning.
Uh-huh.
I guess that would
Like
be
any meaning, like
interesting.
for example, in mathematics, that's the main working horse in mathematics, right? You have variables, like x is a variable, y is a variable. You can denote by x anything. It's a universal symbol, like not only any number, but any function, any operator, any mathematical thing can be named x. Any mathematical object can be named x.
Mm-hmm.
Any process. The same as for y and for whatever. And the main question here, which is Einstein was more interested really, why the hell can we use symbol, like taken from whatever you want. You take some symbol, right? Why it can represent something else? This is the main question of the universe, as Einstein tried to resolve or to comprehend this. The same thing for any other symbol. Why symbol can represent reality, and we talked about it a little before, right, in the previous lecture. So, but the main thing is that they are things, they can be denoted. You can denote anything by x or by y, and it works because there is a similarity, the fundamental similarity between things in the universe. And this fundamental similarity, which is called fractality or whatever, it's working for this. So in this language, they're the same thing. Any sound, or maybe like some syllable, or maybe some word, like, or whatever, or sentence, they can represent anything. There's a freedom of representation. But when you take this freedom in the beginning, you including next some relations between like A and A, right? Or maybe A and U or whatever. Between them, there's certain relations, which are ruled of grammar. And these relations, they should be similar to the real relations which these things which are denoted, the things that are denoted by A and A, the relations between them should be the same. They should represent the same relations in reality. Mm-hmm. So the actors should play well. So this actors A, U, and whatever, or words or whatever, they should play well in this theater. When you look at it, their relations should be similar. They should represent the real relations. Like these represent the real things, the relations should be representing the real relations in reality. And that was this dialectical system, dialectical grammar, that it actually is doing, actually, in this language. That what it is doing. Only because of this, you can use all these phonemes and syllables and words for different stuff totally. And the specialist one can, in a certain way, understand the specialist two. But one specialist can be talking about, like, for example, about quantum fields, right? And but using the same syllables, like yeah, right? Like, remember this, like T to S, right? Time to space, right? So this A and this A, and the relations would be a the syllable representing transformation from T to S, from time to space. But the same syllable can be used in the goods, right? Good to money, right? And again, this be represented by AR. And because the thing are involved in the same relationship, they are actors in the same system, they can be used as a communication tool. So this guy said this guy heard this sound, right, this syllable, but he interprets it like goods to money, but the originally it was said time to space. But because the whole rules are the same underneath this, both understand something. They understand the picture, the universal picture, or you can say self-resemblance picture of reality. This guy understands this, and this saying something meaningful to this guy, and it may be helpful because this guy, if he's using this language, can have some ideas in his own field of work, right, or thinking, and this guy maybe not. For some reason, he maybe didn't think about it, and he suggests him something, and he will understand, but he will interpret it in his own field, in his own context. So this is context 1, and this is context 2. So the whole thing, coming to this particular point, it gives you ability. This language gives ability for any kind of specialists in our world. There are thousands and tens of thousands of specialists, right? Which right now they don't understand each other totally. They don't understand each other. One is speaking about one thing, another thing, each doing the same thing, and they cannot help each other because they don't understand. They're using it with different terms, right? But if they use the language, they may not only understand, but they can help each other, they can have meaningful conversation. And actually, in this way, each of this person will be, in a certain way, universal thinker. Because he can use this system, he can talk not only to other guy, he can talk to himself. Like he goes to the certain field which is not known to him. Like, for example, economist comes to for some reason, he decides to understand what is going on in space-time. What the hell? I didn't never heard about it. I want to know. He opens the book and he said the same words there, which he used, like the same words, same syllables, everything, right? And they are connected in the similar way. In some ways, maybe there are some differences, but this will give him the idea that in his field can be useful too, to understand it from that side. So he can understand more his own field, deeper, by reading books from other field, and at the same time he's starting to understand the field that he never run before, and much easier. Actually, mathematics has this ability to a certain extent. Of course, like these things, right? Like quadratic equation or whatever, right? They use in a lot of really applications. So you can use them. This because of this isomorphism, but it's still restricted because not all the things are quadratic equations, right? We have differential equations. They give more in mathematics. So mathematics has this ability to a certain extent, but not that much. The language has universal ability. This language has universal ability for any specialist to understand each other. So in the future, I have no doubt that this is language of the future. If we are meant to survive, I mean humanity, right? If we survive, so this will be the language of the future. For example, because in this way we can unify all kind of thoughts, all kind of way of thoughts, and help people to help each other in a very, very powerful way. And not only each other, but because communication goes not only in the from one guy to another, but inside the brain. Actually, the consciousness of the brain, it is talking to himself, right? So it's A talks to A, and when it talks, it changes. So it's when you talk to yourself, it's already talking not to yourself, but something changed yourself already. Probably you understand this, right? When you talk to yourself, when you think about something, this is the process, recursive process, which changes you and changes the thing that you are talking about and you are thinking about. Because you're thinking deeper and deeper, you're taking different things into considerations. It goes, changes, and with each circle of returning to the thing, it enriches itself, and you enrich yourself by thinking. You become smarter with each loop of thinking. You become smarter. So what else can I say? Probably that's it. So just to return to it, I would say that interesting enough that the language created for people, and the main goal of this language was to make people smarter. Maybe our future tool to, first of all, to overcome this AI which is coming, one of the small thing. Not only this, but one of the powerful tool for that. And on the other thing, it can make also the quantum computer smarter too, because quantum computing, they can use this language too. And the question in reality is, who will be the first? In this way. There are other ways too, but in this way, definitely. Each thing can be used in a good way or a bad way, right? In a good way, people will use it and become smarter and will outsmart anything, any AIs or whatever, any neural networks or whatever. Because right now, at least right now, each of us has a supercomputer here. Each of us. It's a real supercomputer. Right now, that kind of supercomputers, they have these huge rooms, right? Mm-hmm. And they are not, even with this room, they're not smart enough to really compete with people with everything. They can do many things. They can play chess, right, for example. They can prove theorems. They can do many things. Create music. It all proved. But they still not universal like people are. So we still have some advance. We're still a little ahead. And also there are 4 billions of us here, right? So we still have some time. Not that much, but we still have it. So that's probably all. If you have some questions, guys.
Not for me.
Okay.
You, Franny?
Is it dynamic?
Language?
Yes.
Yes, of course. The whole dialectics, right? Dialectics may be considered as a dynamic logic, like logic as logic of Aristotle, right? Or what we call now formal logic. It's the same, just we use symbols to represent this logic, right? This formal logic is a static thing. Static, if you remember mechanics, maybe, I'm not sure you remember that, there's static mechanics, which considers not moving parts, but just maybe some leverages, some, but static, not moving. And it's very simple. It's not simple, but much simpler than dynamics, right? And dynamical mechanics, that we have laws of Newton laws and everything that we have, all these rockets and everything. This is dynamical mechanics. So the same why I called static dynamic, because formal logic, it relates to dialectics in exactly this way, static dynamics. Logic of Aristotle, it has like any sentence or whatever, it may be true or false. And that's it. Something like a law, right? It is true, right? Something that is wrong, totally negative law, it is false. And that's it. Dialectics says that it's all like fluid, you know, it changes with the time and with everything. So dialectics is dynamical change of true and false. It shows where this thing is true and in other circumstances it may be false, and in which circumstance it may be false. So the dialectics it deals with these things. So it's dynamical things. It's like another example of dynamics, both dialectics and something else. We have these things like becoming, remember, and disappearing, right? And life, like time, right? Like three vectors. Like we have three vectors. It's called basis. It's a geometrical basis. Three vectors, 3 dimensions, right? This we have global basis in a regular way. When people regularly talk about geometrics, we have global basis. So it's a big like axis, like x-axis, y-axis, z-axis, spread everywhere, right? In reality, there's nothing like this. In reality, in space and time is curved. So it's like this. It's curved, curved space and time, and in each piece of it we have local basis. It's called local basis. Like basis here is like this, like x, y, x1, x2, y2, z2, z1, right, d1. So in the other point is this, and this, and again they're different. They're different in each point. So basis is local, so it depends upon the place. Where is it? And the place is the circumstances. Here circumstances are different than here. Context is different. Here is different too. Here is different too. Here is different too. The same thing for dialectics. Dialectics talking about this becoming and dying in time or life, right, of something. But this becoming is different. Here is becoming 1, here is becoming 2. The same thing, here is death 1, here is death 2, and else. So they are dynamic, they changes with everything, with time, with circumstances, with many other parameters. So this is dialectic thing, and the language too. The same thing, like we say, like AR, like for example, it represents becoming, right? But becoming of what? Depends upon what we mean under A, right? Under R. So maybe becoming of the sun, or becoming of the universe, becoming of a person, becoming of an insect, worm, whatever, right? Or it may be becoming of nothing. In this case, it's actually death. It's not becoming, but it's opposite, death, actually. So opposites are turned into each other too. This is dialectics too. Oppositions, they transform into each other. But it is one part. But it's all about dynamical transformation. That is dialectics and the language, and the other language. Yeah.
You said, I don't know if I got it right, but you said people can use different variables to represent something. Is that like a thing that needs to... So is that something that needs to happen between two people talking this language? Like they have to define what things represent.
Exactly.
So they define.
Usually it's defined by context, right? So if we're sitting in the room, right, we have the context of the room. If I say sit at the chair, there's only one like chair here or here. Maybe you may mix chair with the sofa, but usually you'll think of this one. So the context actually it collapses your freedom of choosing, right? But if you want talking about different contexts, you should explicitly say that. You should say first, let's talk about football, for example, or let's talk about economics, right? Or let's talk about quantum fields, let's talk about chess. And then, if you talk about chess, then each person, if they have certain, certain relations, if it has experience with the chess, he will have certain things in his mind. So you're right. You should define your context if you want to talk about particular things. But if you don't want and you talk in general, you may not define it. And in this way, each will understand the thing in his own context, in his own things. It may go to the misunderstanding, of course. It depends. But this again, probably in the real usage of the language, probably you should say, let's talk about our own fields. Okay. Like
so then example, you would define.
So then you define that I'm talking about my own, and I know that you will be understanding in your own. Something like this. So it's definitely new things, but not that new, because actually in many ways we use regular language in a certain way, and actually it's a way to real good ideas, insights and everything. That is called thinking by analogy, like the famous legend of Newton. Probably you heard that he was sitting under the tree and the apple struck his head. Maybe you heard this. No? You haven't heard this? Huh?
I don't know this one.
Oh, this is the story how he discovered.
That's the classic idea. Like an apple fell on him.
How he discovered the laws of gravity. So this like apple struck into his head, right?
Mm-hmm.
Did you say Africa or something?
Mm-hmm.
So yeah, that's so circumstances. Yes, circumstances. Localization. Mm-hmm. I answered this.
Mm-hmm.
Any other questions?
I have not so much of a question, but a challenge.
Mm-hmm. Challenge, okay.
How do you think we all grown with logic, right? Aristotle logic. This is what we've learned from our parents.
Right.
How do you get from Aristotle logic to dialectic?
Okay, the easiest way, if you raise your children in this.
Right, but
yes.
We're not doing that.
Yes, we're already grown up, right?
Yeah.
The other thing is that our subconsciousness is actually dialectical.
Mm-hmm.
It's not using Aristotle logic. Logic is conscious logic. It is learned. It is learned that it's actually accepted by humans at the age, believe it or not, 11 years old. Only at 11 years old, it's very well known number for child psychologists. Children really starting using logic. Before that, they are talking like logic, but when you ask them, they do not use it. They do not understand. They're just taking patterns of logic. They're using these words like if, else, very easily. It looks like they understand it, but it's not. It's checked and it's tested many times, but they start to understand at 11 years old. So before that, children are dialectical. So they're dialectics, believe it or not. And I checked it. Yes, if you try it, children are very easy to take the idea of oppositions that are the same. That's very easy for them. Believe it or not, it's very easy, and they can talk about this, no problem for that. They don't see this contradiction yet. The idea of contradiction, which is main thing maybe in Aristotle logic, right? There is are and not are. You know this, right? Negation of are, right? Mm-hmm. And there's nothing in between. There's nothing. This is Aristotle logic. Dialectics is not like that. It says, yeah, there are lots of between, and also are contains some of negative are. It's easy to say because if you're trying to define something like A, right, you have a border. This border is definition, because everywhere else it is not A, not A, not A, not A. Everywhere is not A in a certain way, and A only here, right? And this border, which gives you the line between A and not A, right? This border is, in many ways, it is fractal. It's not like a regular border even, because you can find some nota here, some nota here, everywhere, and some of these go like this. So the border is actually like this. It's a fractal line. So it's very paradoxical and very interesting thing. So the whole definition of A goes from this not A. So you cannot define A without defining not A, and lots and lots and lots and lots of other things. This first thing, and the second thing is how to come to the regular person, right? You just learn. There are different ways. You may learn dialectics. It's a very, very difficult way. Dialectics is a very complex thing, really. The philosophy, dialectical philosophy, is very complex philosophy. It's very ancient, right? It's ancient, and because it's ancient, it's advanced. So since these thousands of years, it was advancing, and now it's very much advanced. Lots of people right now in philosophers, they do not understand dialectics. Just do not. They cannot think in this way. So it's a difficult way. The easier way is to learn language. Language is much easier to learn than philosophy, believe it or not, because there are certain rules that you use, and actually this language is pretty simple at first in the beginning. Maybe difficult to go to the advanced form, yes, but the simple way is very simple. The first thing of it. And there are other ways too. There are other ways, but this is not for this lecture. This is the advanced way of teaching. So you should deal with your brains like a real and neural network. How you deal with this neural network, and there are certain ways, pretty effective, much more effective than regular teaching. They exist. They can be applied, and also they can be advanced. Right now, people don't really think about it. Mostly people think about how to teach these neural networks. They don't really think about how to teach people. They think that it's okay right now. Go to the school and learn it, right? So, and the school is very, very, very primitive. Modern school is not advanced at all. Should be advanced. There are different ways. One of the ways, by the way, which is, I think, pretty perspective, we can use our, you would say, enemy, right, as our friend. We can use AI. We can teach AI, like for example, this language or whatever, and then AI can teach many, many, many people. One AI, for example. It is a way to. I'm not sure that it is safe, but you can try that. At least maybe in some closed community. I don't know. So there are ways. There are certain other ways, psychological ways. There are many approaches to these things. So it can be done. It's not easy. It can be done. If people want to do something, they will do it.
Fair point.
Yeah. No, we have we have reasons to believe. We'll win. Okay.
Good.
Okay, guys. See you in the future.